Good morning, students. Today we're going to start on section 5.4, which is on multivariable polynomials. So what's a multivariable polynomial? Well, it's something that looks like this. 2x cubed y plus xy squared plus 7x minus 3. And what you can see is that this polynomial has multiple variables in it. And you can have 2 or 3 or 4. Most of our work today will be with 2 variables. And what we're going to focus on is we're going to focus on how to add, subtract, and multiply these multivariable polynomials. And what you'll see is that the way we do that for these is very similar to what we did before. So before we actually get into the mathematics, let's look at the vocabulary just for a minute. So here we have a polynomial in 2 variables. Again, we could have them in 3 or 4. But the terms of the polynomial, always look like this. They look like a x to the n, y to the n if we have 2 variables, or excuse me, not y to the m, y to the m. So, and what happens with this if we have this? Well, the a's, I don't like that color. The a's are called the coefficients. So, coefficients. And so in this case, our coefficients are 1/4, -2, and 4. All right. If we even had a constant term, then that would be a coefficient as well. So those are our coefficients. We would call, if we had a constant, we would call it the constant coefficient, right? The next thing then is we want to look at the degree of a term. So the degree of the terms. Now, if you remember from before, the degrees of a term with a single variable was always the exponent on that single variable. Okay? So, for instance, if we had x cubed plus x squared plus x minus 1, something like that, then the degree of the x cubed, the degree would be 3. The degree of the x squared would be 2. The degree of the x, that's x to the first power, would be 1. And the degree of the constant term is 0, because we could write it as 1x to the 0 power, and x to the 0 power is just equal to 1. And so in normal polynomials, single variable polynomials, the degree is the exponent on the variable term. However, when we get to multivariables, if we have 2 or 3 or 4 variables, what we need to do is add the exponents to get the degree. So we add exponents to get the degree. And so if we have an x squared y, that's really x squared y to the first. And so the degree of that term is 2 plus 1 or 3. Okay? xy, the exponents on those are 1. And so the degree of those terms are 1 plus 1 or 2. Okay? And then the 4y, which is a y term, exponent is 1. The degree of that is just 1. So all we do is we add exponents to find degree. Okay? Now, we then talk about the degree of the polynomial. We've talked about degrees of terms. what would be the degree of the polynomial? Okay, the degree of the polynomial would be the highest term degree. Highest term degree. So in this case, the degree of our polynomial is 3. Okay, so it's a third degree polynomial. Okay, because that's the highest one that we see. All right. Now, at this point, all we have to do is add, subtract, and multiply these multivariable polynomials. So let's go and talk about that. So here's our first example, 4x squared y plus 8xy plus 11 plus 4x squared y plus 7xy. So what we're looking for again are what we call like terms, all right? And how is a like term defined? A like term is a term where the variables and the exponents on those variables match. Okay? And so typically, like when we did this with like 7th graders, we would have them go, okay, 4x squared y, 4x squared y, same variables, same exponents, right? And we'd circle it. And then we'd do like 8xy and 7xy. And we would do that in color like that and have students match things up. Well, that's true. You guys know me. I always like to look at what the mathematics of that is and not just then add the coefficients at that point. But the mathematics would be we use commutative and associative properties to regroup. So what we'd do is we'd have 4x squared y plus 4x squared y plus 8xy plus 7xy and then plus 11. So using the commutative and associative property to move things, swap places, and then also to regroup, all right, as like terms. Once we do that, then we can do the distributive property where we factor out the common term. And even with multivariables, you can see that if you have a like term, all you have to do is add the coefficients. And so we would just add the coefficients and get 8x squared y plus 15xy plus 11. Now, my guess is you guys can go from here to here all on your own, all right? And see that in your head and put those things together. And I'm perfectly fine with that. I just want you to understand that it's commutative and associative properties that allows us to move things in addition and then regroup them as like terms. And then the distributive property allows us to factor out that thing that's the same. That's why they have to be exactly the same. Otherwise, we couldn't factor that out, and the coefficients wouldn't be left over to add. And this is what shows you just add the coefficients, okay? So that's the basic problem for addition and subtraction both. So let's have you do a couple of problems, and then we'll check them. Alrighty, here's 2 problems. Pause the video, do both problems, and then restart the video. And about 5 seconds from now, I will go through these. Ready, set, go. And so you're back now, so let's go through these. This is a subtraction. Since I have a subtraction right here, When I subtract a quantity, that means essentially I'm adding the opposite of each of those. So I'm going to write x cubed plus 7xy minus 5y squared. And then I add the opposite, which means I'm adding a negative 6x cubed, which means I'm subtracting the 6x cubed. And then I add a positive xy, right? And then I'm subtracting a positive, which means I add a negative. And so that means I subtract 4y squared. Another way to think about this is negative 1 times the parentheses. And when you multiply, that changes all the signs. So I do that first. That's actually my first step. Change the subtraction problem. Make sure I'm only doing one thing. Then I regroup. So x cubed minus 6x cubed plus 7xy plus xy minus 5y squared minus 4y squared. So now I've got things regrouped, so it makes it easy to add. I have 1 minus 6 is negative 5x cubed. 7xy plus 1xy is plus 8xy. And minus 5 minus 4y squared is minus 9y squared. And so there's my like terms collected. The next problem, I would want to write that one out, okay? So I'm going to subtract this, subtract 11x minus 5y from the sum. So I'm going to add these two together. 7x plus 13y plus negative 26x plus 19y. So now I've got those added together. And so now I've written this out correctly. So at this point, I'm going to take care of the subtraction. All right, that's the one I want to take care of. All right, so I look at that. I want to take care of that one. And then I'll collect like terms, all right? So 7x plus 13y plus a negative 26x is minus 26x plus 19y. And then minus 11x plus 5y, all right? So I took a negative 1 times each term, or I added the opposite, either way. Now that I have this, I can group things. So 7x minus 26x minus 11x plus then 13y plus 19y plus 5y. And now I can collect the like terms. So 7 minus 26 is negative 19 minus 11 is negative 30x. All right. And then 13 plus 19 plus 5 is 32 plus 37x. All right. And that's it. All done. So if you can do that, you can add and subtract. Those are typical problems. Let's go on and let's look at multiplication. So first of all, when you multiply polynomials, you have to be able to deal with exponent issues. And so what we really first want to do is multiply monomials, just a multivariable polynomial in two variables where things are raised to exponents, etc. We want to be able to do that first of all. So when I look at this and I multiply this, I can understand this as saying negative 8 times x squared times y to the fourth times 3 times x cubed times y squared. Okay? Now, essentially, if I break this down, since this is all multiplication, that means I can use the commutative and associative properties of multiplication to rearrange this. So I'm going to rearrange it as negative 8 times 3 times x squared times x cubed times y to the fourth times y squared. Now, I'm not doing like terms here, okay? Like terms is what we do when we add. Notice how these are not like terms. But what I am doing is I'm multiplying, in a sense, like we talked about before, things that we can combine. So for instance, negative 8 times 3, I can write that out. I can actually multiply that, and that's a negative 24. All right? And then x squared times x cubed, that's the property where we add exponents. So this becomes x to the 2 plus 3. And this one becomes y to the 4 plus 2. And so therefore we end up at negative 24 x to the 5th power y to the 6th. So what's different about this in terms of multivariable? We add exponents when we multiply things with the same base. But if they have a different base, they can't multiply. We just leave it as x squared y to the fourth, like they left them here. But we can multiply x cubed and x squared and add their exponents and, in a sense, simplify it. So that's what we're doing here when we go through this. Now you can carry this to other problems. So suppose I have 5xy squared times 10x squared minus 3y. If I have that sort of situation, then I'm going to do my distributive property, which will give me 5xy squared times 10x squared minus 5xy squared times 3y. All right? And 5 times 10 is 50. X to the first power times x squared is x cubed. All right? And then I have a y squared. All right? And that's how I multiply. It's not a distributive property. I'm just multiplying things, so I rearrange 5 times 10, x times x squared, y squared by itself, minus 5 times 3, negative 15, x squared, it's x to the first, times no x's over there, so it's still just x. And then I have y squared times y to the first, which is y cubed. Okay? And there's a solution right there. And then, of course, you can do binomials times binomials. All right? So you could do something like x plus 5y times 7x plus 3y. And so in this case, we just do first, outside, inside, last, FOIL. Same thing, 7x times x is 7x squared, okay? Because it's x to the 1 times x to the 1, you add the exponents. And then x times 3y is plus 3xy. And then plus 35xy when we take the 5y times the 7x. And then 5y times 3y is plus 15. And y to the first times y to the first, add exponents, y squared. Okay? Now we have two sets of like terms, so we want to add those together. So 7x squared plus 38xy plus 15y squared. Okay? And so as you can see, the multiplication proceeds forward like it always has, using the same techniques, but then we have to be careful to pay attention to exponent, what we do when we multiply things with exponents. All right? So again, let's try a couple of problems. I'll pause the video for 5 seconds and then you can restart it after you do the problems, check your work. Alrighty, here are 3 problems I want you to do. Okay? And just remember things from earlier lessons. That'll be helpful. All right, ready, set, go. Pause the video. Okay, you're back. That means you've tried these, so let's give them a shot. All right, number 1. So 7xy times 5xy. Now remember, the exponents on x and y are 1. So when we add the exponents, we get x squared, y squared. So 7xy times 5xy is 35x squared, y squared. Okay, that was first. And then outside, 7xy times 2 is plus 14xy. And then inside, negative 1 times 5xy is minus 5xy. And then last, negative 1 times 2 is minus 2. So now we collect the like terms, 35x squared, y squared. Now, this is just an xy minus an xy. So they're like terms. So exponents don't change on like terms. It's just 14 minus 5 or plus 9xy minus 2. All right, problem number 2. If you look at this, this is a difference of squares. This is a plus b times a minus b. And so the result is a squared minus b squared. If you saw that, then you could have just written the answer as x squared minus y to the 4th. A squared minus b squared. If you didn't see that, then you would have multiplied the in-between step and you would have gotten x squared minus xy squared plus xy squared minus y to the 4th. And then these two would have added out and you would have ended up in the same place. So this is a case where if you recognize a special product, can help you do the problem quicker. All right, last one. Again, you take the x and you multiply it times each term. So this is x to the 1st times x squared. So that's x cubed plus 5x squared y, because you'll have an x to the 1st times x to the 1st, plus xy squared. All right. And then you take the y times everything. Again, that's a y to the 1st. So you'll get y x squared, so plus y x squared plus 5xy squared plus y cubed. Now, you have to look at this very carefully. None of these are like terms. X cubed and y cubed aren't the same base. X squared y and y, oh, here we go. Those are a like term. Notice it's written as yx squared, but it's the same as that one. And then in the same way, you have this one, 5xy squared, xy squared. So sometimes they're actually different, but in this case you had some like terms, so we can go ahead and write those. So we'll have x cubed, and then a 5x squared y plus a 1x squared y is, or a 1yx squared. So I'm looking at this one and this one. Okay, those are the same even though one's written backwards. So it's plus 6x squared y. And then now we'll look at this one and this one, xy squared, and we have a 5 plus a 1, so plus 6xy squared, and then plus y cubed. Okay? And that would be the correct solution. Okay? Questions? I think you got it. Sometimes you'll have some more complicated sort of multiplications. So you might see something like xy minus 3 squared times xy plus 3 squared. So it turns out the easiest way to do this is if you square these first, which, and the book says don't do that, but you could. You could say, oh, this is a minus b times a minus b, so it's a squared minus 2ab plus b squared. All right, where this is a and this is b, this is a and this is b, and that one would be a plus 2ab. So I could recognize that, and then what I get is I get x squared y squared minus 6xy plus 9 times x squared y squared plus 6xy plus 9. And then I multiply those. Okay? And so I got to take this times each of these three, this times each three, and this times each of those three. So I'd have 9 multiplications, and then I'd collect like terms. And that's okay. But the way they want you to look at this is how can you make it simpler? And so what you can notice is you could say, oh, this is xy minus 3 times xy minus 3 times xy plus 3 times xy plus 3, which is really 2 sets of difference of squares. So I could actually multiply this to x squared y squared minus 9 times x squared y squared minus 9. And if you multiply this out, you'll get exactly the same thing that you would get if you multiply that one out. And so that, I'll just draw this dividing line here so it's clear. But that leads to observation before doing the work. One way you might do it, and you think it might be easier, turns out to lead to a much more complicated problem, more chance for error. The other way, if you notice it's actually 2 difference of squares, actually leads to a fairly easy multiplication that you can knock out fairly quickly. Anyway, I just want to mention that. I'm not going to finish this problem, but I want to mention it as something that's coming up. Can you recognize things in different forms when they're kind of hidden in different forms? And that's sort of a maturity. So you're assigned one of those that's similar to this, but there are more problems there. It's problems 81 through 85, and you have to do 84, which is similar to this, but I would recommend you look at all of those, and if you have a question, ask them in class. Okay? Finally, the last thing you have to do is a couple of story problems. And the story problems basically start out with they give you a formula. Okay? So for instance, number 87 says the formula for the number of board feet in a piece of lumber is 1/4 x squared y minus 2xy plus 4y, where x is is the tree diameter in inches. That's what x is. And y is the length of the tree in feet, y feet. So x inches, y feet. And you just put them in the formula, and this will help you find the number of board feet. All right? And so on the problem, they say they've cut trees that are 10 inches in diameter and 16 feet in length. So this is equal to x and this is equal to y. And the question is will you have enough board feet? For the job, they need 3,000 board feet. And they have 20 trees like this. So what you want, all you want to do is you want to find the number of board feet for one tree. Okay. That will equal 1/4 times 10 squared times 16 minus 2 times 10 times 16 plus 4 times 16. All right. And so I can figure that out. 10 squared is 100. 1/4 of that is 25. So 25 times 16 is 400. Minus 20 times 16, which is 320. And then plus 4 times 16, which is 64. And so we end up here with 80 plus 64, or 144 board feet for a tree, for one tree. And so if I have 20 trees, so 20 trees of the same size, that means I have 20 times 144 board feet, which is going to equal 0.882, which is 2,880 board feet. So, question, do I have enough lumber to fulfill the order of 3,000? And the answer is not enough lumber. All right. Now, what's a board foot? Just so you know, a board foot is a 1 inch thick piece of wood. It's 1 inch, and it's 12 inches. It's 1 foot wide, and I believe it's 12 inches long as well. And that's what's considered a board foot. And so when you go to buy lumber, wholesale, you're buying it by the board foot. And that's how they figure out how much lumber is in a stand of trees. They'll statistically estimate the average size of the trees and then use that to estimate how many board feet might be in a particular stand. And then they'll kind of calculate it out. And so it's always interesting how they cut lumber. I used to live in Oregon a long time, so I knew a number of guys who worked at lumber mills and who would see round logs, and then they might cut, you know, a 4x6 in the middle, and then a 2x6 and a 2x4, and as you can, maybe a 2x8, and the saw electronically would figure out what needed to be cut and how to cut that log. They'd have a computer, and this formula actually describes how many board feet they can get out of there, and then the saw would find that maximum number of board feet. So it's pretty cool how this kind of thing is figured out, and that type of automation. Anyway, I always saw it as really fascinating and a great application of mathematics. But here's the idea is they're giving you formulas, and then you answer questions using that formula. So that's the kind of story problems you see. And I've assigned you a couple of others there. Alrighty? And by the way, this is a real formula. It's not a fake one. It's real. It's actually real life. Alrighty, that's all I have for you. Bye.